going to kind of continue on, finish up chapter 13. We'll probably also roll into chapter 14 after that. Again, those notes also should be up there if you need them there. So we've been talking about equilibrium. We've been talking about basically how to solve equilibrium type problems um, using ice tables. So remember, we use the ice tables. We have initial, we have change, and we have equilibrium is what basically the ice stands for. Um, we use ice tables really when we're only given sort of initial concentrations to use it to figure out basically what we would have left over when it's all said and done at equilibrium. The change part is really the kind of important part. It takes into account stoichiometry for you as well. It is also really what you're solving for. We usually represent that with an X. We talked about that you could a lot of times assume that the reaction is going from reactants to products pretty safely. Again, one sort of situation where you might want to double check that is like an example I think we did last time. Um, if you are given sort of information about everybody in the reactant in the reaction, both reactants and products, you might want to solve for Q first just to verify that it is proceeding towards the product side. Again, if you're only given reactants in a problem, it's pretty 100% safe to assume that it is going to progress from reactants to products. And again, what that means in terms of the change part is the minuses would be on our reactant side, on our product side would be the pluses in terms of x's. We do put that into our equilibrium expression. We solve for x. Could be sort of a simplest way to solve for it, maybe kind of a perfect square, may have to use quadratic formula like we did last time. Again, there's a lot of factoring and stuff that sometimes happens, and you want to be careful on that. Any questions on any of that stuff that we kind of went over last time? Okay. Okay, so I think this is where we sort of left off in terms of examples. So why don't you take a couple minutes, start working on this one here, and sort of see what you come up with, then we'll talk about it. Here we're actually giving a KP value. We're also giving pressure. So as we talked about a little bit last week as well, it really doesn't matter. You can do pressures in ice tables. You can do concentrations in ice tables. As we talked about, though, you do want to make sure they're in atmospheres, which they are in this problem. So you want to approach it the same way. The only difference is you're really just dealing with pressures rather than concentration. So I want to take a couple minutes, see what you come up with, and we'll talk about how to sort of approach. It doesn't make a difference. You can approach it the exact same way as you do with concentrations, like the ones we've done before. The one sort of thing that you do want to make sure of, just to reiterate that point that I mentioned a few times already, is again, if you're going to do an ice table and you're going to do something with pressure, you do want to make sure that it is in atmospheres. And again, and even in a problem where, as I mentioned maybe earlier last week as well, that they give you the pressures maybe in, say, millimeters of mercury or torr or something like that, and they end up asking you to give the answer in something like millimeters of mercury or torr, but you do need to use an ice table to sort of solve the problem. You do need to convert them into atmospheres, put those atmospheres in the ice table, solve the ice table in atmospheres, and then at the end convert it back to whatever unit you're looking for. So that's sort of an important aspect of when you're dealing sort of with pressures and ice tables. You want to make sure that it's definitely in atmospheres. And again, even in a question where they may not give it to you in atmospheres or want the answer in atmospheres, but if the way you need to solve that problem is use an ice table, you should make sure that they are in atmospheres. Otherwise, you will end up with the wrong problem. So that's sometimes people run into a little bit of problems with that. So we're really just going to kind of approach this the same way. So if we look at sort of our pressures in this case, we are given the pressure of our N2. We're also given the pressure of our H2. We're not given anything here in terms of our products. So much like a lot of our assumptions here, we can assume that probably this reaction is heading towards the product side in this particular case. So we'll start with our ice table here. So we'll have our N2 plus our 3H2 going to our 2NH3. So initially, we have 0.862 in terms of our pressure. We have 0.373 in terms of pressure there. And again, since we were not given anything there on our product side, we're going to go with 0 in terms of that. Change here, the important part is we just talked about, again, since we weren't given any products, we are assuming that the reactants are going to products. So this is going to be minus x here. This will be minus 3x again for the coefficient. This would then be plus 2x here, also again for the coefficient. So as we talked about before, very important to make sure you include those coefficients. Otherwise, again, you really will have the wrong stoichiometry mole-to-mole relationship, and you really won't get obviously the right answer here. Like normal, we're just going to kind of carry everybody down here. So that gives us 0.373 minus 3x and 2x. First off, any questions on the ice table, or any numbers came from, or anything like that? So just like we've done before, what we really want to do at this point is use our equilibrium expression, which is K is equal to NH3 squared divided by N2 times H2. We also need to cube that thing, and that will equal our Kp value, which was 4.31 times 10 to the minus 4. So we're going to take our equilibrium stuff there and put it in. That will give us 2x squared up on top, going to equal 0.862 minus x times 0.373 minus 3x, and we still need to cube that thing, and that's going to equal 4.31 times 10 to the minus 4 in this particular case. All right, so we need to solve this, and clearly at this point, that looks like a lot of math that nobody really wants to do, I'm sure. So clearly the right answer here is, go to the next problem. Next one might be better, I think. But in case you really do want to solve it, let's think about a way that we can maybe solve it where you're not going to do a ton of math here. So even if you know how to sort of solve something like this, we can look at a couple of things that were in this problem to sort of help us maybe find an alternative approach. And the main thing is, if we look at our equilibrium constant value here, that is 4.31 times 10 to the minus 4. That should tell us that that number is relatively small, right? So that is a small value of K in this particular case. When we do have a small value of K, what that tells us is when we reach equilibrium, we should mainly have reactants present. So this is what we mainly should have once we reach equilibrium. So what does that mean for our change? What that means for our change is we would expect our change, which are our x's here, to be relatively small, right? So the change here is going to be relatively small. Our equilibrium constant is obviously relatively small because of that. And that means that we mainly have our reactants. So in a situation like this where you have a small K value, you can make an assumption. You could assume that X is equal to 0. Now, clearly you can't go crazy and assume every X you see on the page is 0. Otherwise, obviously you have nothing to solve for. So the X's that we're really talking about are the X's that are going to be either kind of subtracted from something, a number, or in some cases, they may even be added to a number, because that change part is going to be relatively small. So those are the guys that we're actually going to zero out. We're not going to zero out everybody here. So this X will actually still remain. Again, we would have nothing to solve for. But the reason that X really remains is that X is basically, this guy is starting at 0. So whatever it made is relatively large compared to where it started from. But what we have here in terms of our reactants is going to be relatively small from where it started from, that change that occurs. Any questions on that so far?
Could you go over that, sorry, one more time? I think I got confused when you went to the reactants and how that's small and how we figured that out, that it was 0 for X.
So really the basis of this is based on really the value of the equilibrium constant, right? So at the beginning we talked about that the actual value of the equilibrium constant does give you information in terms of this reaction as to sort of what's happening. So if we have a relatively small value for K, and remember anything that's small is considered less than 1. If you have a small value of K, that means that when you do reach equilibrium, you're going to still mainly have reactants present. So if we're assuming this reaction, for example, here is going from reactants to products, but when it reaches equilibrium, we're still going to mainly have products. That means probably not too much went to the product side. So we didn't make a lot of change that occurred. And what that means is these X's here in the table are going to be relatively small for our reactants in this case, because we're not going to lose a lot of reactants, right? Because if we lost a lot of reactants, then we'd actually have a lot more products at equilibrium than reactants, and we would have a larger K value. So opposite of that is if we have a large K value, that means that the reaction is basically going to have a lot of products when it reaches equilibrium, which means that the change from reactants to products is going to be significant. So here, when we do have a small value of K, you can make an assumption that the change from reactants to products is going to be very small in terms of how much reactants are going to be lost. And we could assume that those guys are going to be zero because of that. So you could really only do this assumption in a small K situation, which again is anything technically less than one. Other questions on that? Okay. So now that we have our assumption, and again, we're only getting rid of the X's that are really, when you look at a problem, the X's that you subtract or you add them to a number, that's going to reduce this down to something a little bit more manageable. So we will end up with 2x squared up on top. Again, that's not going to change. Getting rid of the minus x here leaves us 0.862 on the bottom. Getting rid of the minus 3x gives us 0.373. We still do need to cube it, so you don't want to forget that part of it. And that's going to equal 4.31 times 10 to the minus 4. So this is going to be a lot easier to solve, obviously, than what we had previously. So basically what we want to do is kind of multiply those guys together and then multiply it to the other side. So I'm just going to do all that together in sort of one move. And if we do that, 0.373 cubed times 0.862, and then times 4.31 to the minus 4 gets us times that. Looks like it gets us 4x squared, which is what's left from on top, equals 0.00001928. We're going to divide 4 to both sides and also do a little square root action on it as well. And if we do that, divide by 4 and take the square root, it looks like we end up with an x value of 2.2 times 10 to the minus 3. Any questions on that? Okay. So obviously we can make this assumption, makes the math a little bit easier, but there is a rule that we need to follow if we decide to make the assumption. Now, the assumption will not be sort of correct in all situations. There's a lot of things that sort of depends on whether or not it will actually come out okay. And there's a couple of different ways you could kind of check to make sure your assumption's okay. We will in this class, we'll use what is sometimes referred to as the 5% rule. So we'll use the 5% rule to help us determine if our assumption is okay. And basically to do the 5% rule, basically what you do is you take whatever X value you got and you divide it by what you were going to subtract it from. So you take basically I'll put up here, take the X value and divide by what you were going to subtract it from. So for example, our X value here was 2.2 times 10 to the minus 3. And if you look at the equilibrium line of your ice table, one of the things we were going to do was 0.862 minus x. So we would divide it by 0.862, which was our initial concentration, or pressure, I'm sorry, times it by 100%. And if you do that, and you punch it in right, there we go. you end up with 0.255%. That is less than 5%. So this assumption is good. So our assumption is good because we are less than 5%. In my experience, if you check one of the reactants, you're probably okay with both of them, but you could do the same thing for the other reactant. You could put it back in there and, take 3 times 2.2 times 10 to the minus 3 and divide it by 0.373 if you wanted to, and you would see it's okay as well. So you could check both, but usually if you just check one, you're usually pretty good. So again, even if you kind of did the other one, times it by 100%, I think you end up with maybe like 1.77% or something like that. Also okay as well. So, like I said, usually if one of them is good, if you check it, you're probably okay. You don't have to kind of check them all. You'd probably be okay in that particular case. So the question is, what happens if we check it and it's over 5%? What happens if it's over 5% is technically what that means is the change was relatively significant. It wasn't insignificant. And that means you need to go back and solve it some other way. For our purposes, that would be probably something like the quadratic formula. You would need to kind of solve the in that sort of sense. Any questions on sort of checking it here? Okay. So now that we made our assumption, we checked it, it's all good. We now have our x value that we could go and put back in to our equilibrium line. And oops, let me go here. Oops. So putting back into our equilibrium line here, we have that the pressure of N2 would equal 0.862 minus 2.2 times 10 to the minus 3. And that's going to get us, looks like 0.860. And again, these are pressures. So this is going to be atmospheres as the unit there. The pressure of H2 would then be 0.373 minus 3 times 2.2 times 10 to the minus 3. And that's going to get us, looks like maybe 0.366 atmospheres. And lastly here, we have basically NH3. So NH3 would equal R2 times 2.2 times 10 to the minus 3. We'll go up. And 0.2 looks like 0.00 or 4.4 to the minus 3. Let's do the scientific notation as well. So 4.4 times 10 to the minus 3 atmospheres. And just like before, you could put those values back into your KP expression. And again, it should give you a KP value that is obviously pretty close to what was in the problem. And if you do that, it does look like you end up with 4.6 times 10 to the minus 4. So pretty close. Again, with rounding, obviously going to be off a little bit, but in the same ballpark. Any questions on any of those there? So this is another approach that you could do with ice tables. Again, it could only be used if the K value is small. So it does have to be a small K value in order for you to try it. It will not always work. So you do want to make sure that you do check it using that 5% rule. The other option is you can ignore the assumption and solve it using the quadratic formula and just go straight through that way. You should get the same answer if you want to go and do the quadratic formula. it can obviously save you some time to do the assumption. This is also why, if you look back on the previous three examples that we did, we could not do the assumption on any of those. The first one had a K value, I think, of 7, which is obviously larger than 1 and a large value. And the other two examples that we did was 54.3, which is also a very large value for K. And in both, all three of those cases, that would imply that we would mainly have reactants at equilibrium. And that means that the change from reactants to products would be significant, and you could not do the assumption. So again, that's why we did not do the assumption on the previous ones. Any questions on ice tables, how to solve them? So we've now seen a few different ways using the quadratic formula, kind of like a perfect square. And here doing the assumption is another way. Again, these will be the ways we probably will solve these problems in this class. There is sort of another way. Again, I might have mentioned it before, but just to remind you, there's something known as successive approximation, where you sort of make a guess as to what you think the x value is. You put it in, solve for x, and you keep kind of doing that process until the number you put in is the number that you get when you solve for x, and then you get it. And again, that could be an all-day project if you're not very good at it. So we won't be doing any type of successive approximation sort of problems. So basically, those are the three ways that you will solve these type of problems. Any questions on any of that there? Ice tables in general. And again, sometimes people don't want to check their assumptions. You do want to make sure you do check your assumption. It may be a bad situation where it's like just over 5 or 6%, pretty close. But still, technically, if it's over that 5%, you got to go back and solve it some other way. Any questions? Okay. Then let us talk about, I'll scroll this across the screen, pretty much what we just did. Hopefully, good. And again, how to check it as well. All right, so the last thing we're going to talk about in this chapter is basically LeChatelier's principle. And LeChatelier's principle is the idea really of we have really a system that is at equilibrium. And basically, what we do to it is kind of screw it up. So we add a stress to the system. By adding the stress to the system, it kind of messes up the equilibrium. So really, in this situation, you have a nice system. It's at equilibrium. And again, what that means is it's going to be going from reactants to products just as fast as going the other way. We add a stress to it, messes up the equilibrium, and then it wants to once again get back to equilibrium. And really, there's kind of three ways to do that. Really, there's two ways to get back to equilibrium, but there's three sort of situations that could occur in that. One situation is they need to kind of shift to the right and basically make more products to reach equilibrium. Sometimes it may need to shift to the left after some type of stress is added to it, which means it needs to make more reactants. And there is going to be some situations where, regardless of sort of adding a stress to a system, it will have really no effect and there will be no change that will occur. So these are, really the three sort of things that could happen in a LeChatelier sort of principle problem. You'll do something, it'll need to go to the right to make more products. You'll do something, it needs to go to the left to make more reactants. And again, the goal here is to get back to that situation where the rate of the forward reaction will equal the rate of the reverse reaction. And again, there'll be some situations where really nothing will cause it. There'll be really no change that will occur. So what are some stresses that we're going to sort of talk about? Concentration, pressure, and volume, changing the temperature, adding a catalyst. These are some stresses that you can basically do to a system that is already at equilibrium. And again, it may cause something to occur. All right, so let's take a look at first couple things here. take a look at concentration first, I think. I'm just going to write some more notes, I think, and then we'll pick back up with what's on the slides, I think. All right. So the first thing is concentration. And really, you could do one of two things with concentration. You could either add or remove. Right? So those are basically your two things you could do. When we add something, more concentration, it will cause it to shift away from the side it was added from. So when we talk about sides, we're really talking about reactants, right? And products, right? So that's pretty simple. If you have a reactant, you go to the shelf, you pick up the bottle, you dump it into the beaker, right? You just add more reactants. Maybe you go to the shelf, you pick up a product and dump that into the beaker. You added more products. So add away AA is a good way to remember that. It adds away. It will shift from the whichever side it was added to the other side to once again reach equilibrium. The opposite is true. If we remove, it will actually shift towards the side we removed it from. So what that means is if you remove a reactant, it would go towards the reactant side. If you remove a product, it would go towards the product side, and basically it goes towards the side. So just to sort of illustrate this, if we want to remove something, right? How do we remove something? Say that's a solution in a beaker. Do we just reach in and grab it? The answer is no, you shouldn't reach in, obviously, and grab anything. So there's really two common ways. I think there's a safety video on that. Don't do that. There's two common ways you could kind of remove something from sort of a equilibrium. And really, if you think about it, what we're really talking about is, you have probably like a beaker sitting there, right? And there really is no obviously left hand side, right hand side of the beaker. But you basically in that beaker, because it's a system at equilibrium, have both reactants and products floating around in there. So you have both, reactants floating around, you got products floating around in there. And when we talk about sort of adding something to the right hand side, left hand side, you can look at the balance equation and go, oh, okay, so on the left hand side, it's going to go to the right hand side and vice versa. So, two ways that we could really usually sort of remove something from a beaker like that is to form a precipitate, PPT precipitate. So we could add something to that beaker up there on top of the page that will react with something that's floating around in there and make a solid. So when we make a precipitate, which is a solid, as we talked about before, solids do not really participate in the equilibrium, right? So it's going to kind of fall out. So it's like reaching in there and grabbing something out of the solution by making a precipitate. So that's a very common way we could remove something. The other sort of common way, and obviously if you make a precipitate, you could see it happening in most cases. Obviously you'll see maybe a white solid, green solid, yellow solid, some type of solid being formed. Another common way we could remove something is actually making water. So the formation of water. So if you have a reaction where perhaps there's H plus involved, or maybe there's OH minus involved, and you add either H plus or OH minus to it, those two guys will come together and make water, which is H2O. H2O is a pure liquid, not involved in the equilibrium as well. So that's, again, another common way that you could kind of reach in and remove something from the solution. Again, usually involving the presence of like OH minus or like H plus or H3O plus sort of there. And basically the formation of water is another very common way. That visually, though, you usually can't see it, right? So if you look at it, you won't be able to tell, oh, it's, I made water, because it will look kind of the same. But the formation of water, obviously is one way, really not visually that you could probably see something happening, but it is another way to remove something and cause that reaction to shift. So, if we just kind of think about these things just in some wonderful stick figure drawings, if we had, say, a couple of stick figures up here on a seesaw sort of deal. We'll call this guy the reactant side, this guy the product side. If we throw somebody on the product side, for example, what's going to happen is, somebody kind of hopped on this side. This guy is then going to go up in the air, not be happy about it. So, in order to fix that, we need to put more people on the opposite side, away from the side where we added. And we would once again come back to sort of equilibrium. It's advanced stick figures when you put faces on them. There you go. That's part B of the class in stick figure drawing. There you go. So we were at equilibrium here. We added more products. It needed to shift to the reactant side to make more reactants to once again reach equilibrium when we get to this side. Same thing could happen again if we sort of do the opposite and remove somebody. So again, assuming this guy is my reactants, this guy over here is my products. Let's say this guy decides I'm going to hop off. When he hops off, this situation is going to occur. And now to fix it, we actually need to shift towards the side that was removed, right? And we will once again come back to equilibrium, and my seesaw gets all messed up here. It was bad drawing here. And we're back to happy faces, hopefully, in terms of equilibrium, and once again reach it. So when we add, it goes away from whichever side. So again, if you add more reactants, it will go to products. If you add more products, it will go to reactants. And if we remove it, goes towards it. The real reason that sort of happens is a couple of things. If you add, say, more reactants are available to start that reaction, and that's going to kick off the forward reaction to occur. If you remove some reactants, that means you're going to have less reactants, more products. Products will probably, the reverse reaction would be favored heading towards the reactants. Any questions on concentration there? Another effect would be, say, pressure and volume. They're kind of related to each other. They're oftentimes sort of interchanged, and they really involve a situation where we're dealing with gases. So if you remember perhaps some gas laws, somebody like our good friend Boyle, maybe, the relationship between pressure and volume, as the pressure goes up, the volume goes down, and vice versa. As the pressure goes down, volume goes up, right? So that inverse relationship to each other. And that's a good way to sort of think about it, is if my pressure increases, that means my volume decreases. So basically what's happening is my pressure is going up. I want to kind of fix that. I want to bring my pressure back down. So if you think about it, in a smaller volume, we would need less gas molecules. So what will happen here is it will shift to whichever side has the least number of gas molecules in that situation. Obviously, that depends on the actual reaction you're looking at, as to, is the left-hand side more gas molecules, is the right-hand side more gas molecules. So it really is sort of reaction dependent as to which way that is. Opposite is true. If we kind of drop that pressure down, volume's going to go up. And in a bigger volume, we would actually need, so pressure comes down to bring the pressure back up. We need more collisions, and we would need more gas molecules. So shift whichever side has more gas molecules. Personally, I usually think about volume when I'm thinking about pressure and volume in this situation. Small volume, less gas molecules. Bigger volume, more gas molecules. And that's usually a good way to, if you understand, again, the pressure volume relationship, think about volume, and that usually will get you to the right answer. So again, in a small volume, small area, you want less people crowded in there, right? In a larger volume, you need to kind of fill it up with more people. And in this case, we're talking about gas molecules. And how do we figure that out? It's simply looking at the balanced equation, right? And looking about anybody that has a G next to it, basically, right? So in this case, this would be 5 gas molecules on this side. This guy would be 2 gas molecules on this side. So obviously, depending on what we would do here, it would either shift to the right or the left. So, if we increase the pressure, the volume would get smaller, which means in this particular reaction, it would actually shift to the right, which has 2 gas molecules. Again, the right-hand side having the least number of gas molecules. And again, this is really only with things that have the gases or G. So if you had, aqueous or solids in that reaction, you wouldn't count them, just the guys with the G's. Any questions on pressure and volume sort of changes? Then the next sort of effect is temperature. And as we talked about, temperature really is the only thing that will affect the actual volume, not the actual volume, the actual value of the equilibrium constant. Temperature works the same as concentration. So if we increase the temperature, it will shift away. And if we decrease the temperature, it will shift towards it. So how do we know, this is away, this is towards? Well, it really involves whether or not the reaction is exothermic or endothermic. So we'll start with exothermic. Exothermic, a reminder, is when heat and energy is released, oftentimes displayed by delta H, which is the enthalpy. And the enthalpy value for an exothermic reaction is a negative value. And what does that mean? It means that if you were to write a reaction, heat and energy would be considered a product. So if it's an exothermic reaction, heat and energy is considered a product, which means if you increase the temperature in this situation, it would shift away from the product side. If you decrease the temperature, it'd be like removing the heat and energy, which is a product, and it would shift towards the product side in that particular case. Any question on that one there? The opposite of exothermic is endothermic. So if you have an endothermic reaction, heat and energy is absorbed. Also means a lot of times that's given to you as like a delta H value. Delta H value would be positive in an endothermic reaction. And what that means is if you were to write that same reaction, heat and energy would be considered a reactant in that particular case, which means the opposite. If you increase the temperature, you're adding reactants, it will shift away. If you decrease the temperature, be like removing reactants, it would shift towards it. Any questions on temperature there? So it's important to obviously figure out really in terms of temperature, is it a exothermic or endothermic reaction? And I would say probably in most cases, especially book type problems and those type of things, you're oftentimes given an equation and like the delta H value next to it. The delta H value, the actual value doesn't really matter. It's really just the sign that matters. So either it's negative or positive, allowing you to figure out exothermic or endothermic. Any questions on that there?
I had a question for you real quick. So with the exothermic and endothermic, are the indicators kind of where the heat is? If the heat's on the product side, will it be exothermic, or is that also like could possibly change because if it's a reverse reaction or
I would say in this sort of aspect of it is if it's an exothermic process or reaction, and again that could be signaled to you by a delta H value that's negative. What that means is the heat will definitely always be considered to be on the product side, regardless of sort of if your question is regardless of sort of which way it's actually heading the reaction. So the idea here is, you know, this reaction in this situation has already reached equilibrium. So it's sitting at equilibrium where the rate of the forward and reverse reactions are basically equal to each other at this particular point. But then what you might do to it is either increase the temperature or decrease the temperature. So if that reaction that's sitting at equilibrium is a exothermic reaction, by increasing that temperature, it can be thought of as heat being a product in that case. And it would be like you were increasing the products, which we would expect that process of increasing the temperature to kick the reaction to head towards the reactant side away from the product side in that particular case. So if you see something that says exothermic, 100% safe in this sort of situation to assume heat is always going to be considered a product, heat, energy, temperature, however you want to think about it. And again, that's basically like concentration. Either I'm going to increase it, which is adding to it, which causes it to shift away, or I'm going to decrease the temperature by putting like everything on ice, which would be like removing a product and it would go towards the product. And same thing for endothermic as well, it'd just be on the opposite side. Other questions on that?
thank you.
You're welcome. Okay. So, like I said, usually a lot of times delta H given to you as either positive or negative. You may actually see heat written into the equation, kind of like what I wrote up here. You may even actually see sometimes a number given to you, like an energy number, this many calories or kilocalories or this many joules. And again, that would be given to you probably if it was written into the equation, either on the reactant side or the product side. And again, depending on which side that is, that will allow you to know that is either exothermic or endothermic. Other questions on temperature? And again, as we talked about temperature, changing temperature is really the only thing that will change the actual value of that equilibrium constant. The other couple of things that you could do is you could add a catalyst. A catalyst is not a reactant. It's not a product either. It's not used up in the reaction. It is there just usually to speed up the reaction. There are catalysts that actually can slow down reactions, but in most cases, most people, when they think about a catalyst, think about it in the sense of sort of speeding up the chemical reaction. When we do add a catalyst, it essentially will cause no change to occur. So that's a possible situation where you would have no change occur. You'll just get to equilibrium quicker. Nothing much is going to cause to go left or right. It's because it's not really a reactant or product. So adding catalyst really will cause no change to occur. Other kind of things that could cause no change, things like, maybe adding a noble gas, right? Noble gases are chemically inert. They pretty much will cause a no change situation to occur. Any questions on that there? So these are sort of the main points here. Let's look at some here and just kind of do some examples maybe. So this is what we sort of talked about here previously. The system again will shift away from added concentration towards whichever way you remove it from. Temperature again is really depending on exothermic or endothermic, like we talked about, as to which way it will go. Pressure, again, pressure and volume oftentimes tied to each other. Good way to remember those, like we talked about, is kind of think about it in terms of the volume. Again, smaller volume, you need less gas molecules, larger volume, more gas molecules to fill it up. Let's see here. So let's take a look at this reaction here, and we'll just do some here and see what we got. Let's say, for example, might probably not be right, but we'll say that this delta H is negative 135 kilojoules, which is definitely not right, but we'll just do it for this example. And let me just give you some scenarios and you tell me, is it going to shift to the right? shift to the left are no change. So let's say and I'll do a bunch of them here and then you can think about them. Let's say we added NH3, we removed H2, we increased the pressure, we decreased the temperature. Um, let's say we added N2, we increased the volume. All right, so take a couple minutes here, think about each of these, decide will it shift to the right, will it shift to the left, will there be no change, and then we'll talk about, see how you did. It goes away, so it should shift to the left in this particular case. Um, if we remove H2 over here on our reactant side, when we remove it goes towards the side we removed it from. So it also should head to the left in this particular case. If we increase the pressure, remember, if we increase the pressure, really what that means is that the volume is probably decreasing. And when the volume decreases, we want less gas molecules. So on this guy here, we have 4 gas molecules. On this side, we have 2 gas molecules. So it should actually shift to the right in this particular case because of that. Decreasing the temperature here, again, we would want to look at my made up delta H here. The important part is the sign. So it's negative, which means that this reaction would be exothermic, which means if I wrote in heat and energy, it would be on the product side. So by decreasing it, it would be like removing a product. And since temperature works the same as concentration, it would then shift towards the product side in this particular case. Adding N2 is adding a reactant. So again, add away. So we added a reactant on the left-hand side, should cause it to shift to the right-hand side. And lastly here, increasing the volume will actually drop the pressure down, but important here is bigger volume, more gas molecules, which means should go to the left. Any questions on any of those there? Okay, hopefully you got those. So let's take a look at a few more here. We'll skip what's written here. It's not that important right now. We'll skip this one here. Let's take a look at this one. I think it's missing a coefficient on yours. So let's do a 2 there. Missing on mine too, probably. It might not be on yours, but it should have a 2 there. So let's do a few more here. So let's do, let's say we increase the temperature, we decrease the volume, we add O2, we remove N2, we add NO. Let's say we decrease the pressure here. And let's just say we add a catalyst here. All right, take a couple minutes, see what you come up with on this one. Okay, so let's take a look here. So we're going to start with temperature on this particular one. It is endothermic. So endothermic means a couple of things here. It does mean that if you had a delta H value, it probably would be a positive. Also means that heat and energy would be on a reactant side here. So if I increase temperature, that means I'm increasing reactants, should cause it to shift away, will cause it to shift to the right in this particular case. I'm going to decrease the volume. So if I decrease the volume, that means really the pressure is going to go up. On the reactant side here, looks like grand total of 2 gas molecules. With the proper coefficient there, actually 2 gas molecules as well. That is a push. There is no more or less, right? So this would be a no change situation. Again, there is no obviously more gas molecules or less gas molecules. probably will just kind of maintain where it's at in that particular case. If we add O2, O2 again being a reactant, add away. So it's going to shift away from the reactant side to our product side. And we go to the right. We're going to remove N2. So removing, when we remove something, it goes towards it. And since that is a reactant, it would cause it to shift towards it. Adding NO would be adding a product, add away. So that would also cause it to shift to the left. Decreasing our pressure, going to increase our volume. Again, we typically want more gas molecules, but kind of the same situation as we have here, going to be no change. And lastly, adding a catalyst will also get you no change. Again, we'll just get you there quicker. Question on LeChatelier's principle, how to figure it out. And again, sometimes people get confused about, the idea of left side, right side. And again, as I mentioned earlier, there is no right side or left side. So when we're talking about that, we're really talking about sort of reactant side or product side from the balanced equation. That's sort of how you should think about it as well. Any questions on that?
I'm a little confused why there's no change when the volume decreases while the pressure increases. Because I thought that when pressure increases and the volume decreases, you need less gas molecules, therefore, you'll move to the right.
You do need less gas molecules, but in this particular case, and again, there was a 2 missing here, right, on yours. So with that 2 there, on the left-hand side, there's 2 gas molecules. On the right-hand side, there's also 2 gas molecules. So it's kind of it's a push. There's the same amount on each side. So there is,
Oh, so when they equal each other, there's no change. And then if one
yeah.
has more and the other has less, there's a direction.
Yeah, so
Okay.
so this would be like another example where you could potentially hit like a no change. Again, just simply because there's the same amount on both sides. So if we went back to the previous one, say, or this one, right,
Hmm.
and we did whatever, which one we were doing there, less gas molecules, so increase pressure, right, decrease volume. In this case, there's 4 gas molecules, and this guy there's 2 gas molecules. So there is a difference in the amount of gas molecules that are here. So in this case, in the smaller volume, we would want it to go to the right because
Okay.
the difference just so happens in that particular example there wasn't a difference.
Okay, that makes sense. Thank you.
You're welcome. Other questions? Okay, so that actually is chapter 13. So that's the end of chapter 13. So we will have a quiz next Monday on chapter 13. So we'll do a quiz next Monday. It's a lot of math there, but I'm going to go with the 8th, hopefully. Yeah, so 21 on chapter 13. So anything in chapter 13 through equilibrium, through LeChatelier's principles, ice tables, all fair game. Sure exactly when we'll take it. We're going to take it towards the end of lecture. We might do it at the beginning of lab. So we might do it in one of those 2 spots. So I'll let you know for sure. And how we'll do it. So still deciding which way we want to do it. But the one thing I do know for sure is we are going to have a quiz in some form on next Monday on chapter 13. And again, we'll either do it through proctorial, either at the end of lecture or beginning of lab. We'll just start lab a little bit later, or we'll do it through Zoom, and we'll kind of do it through the Zoom thing. So either way. Any questions on that there? Like normal, again, you will not be given any type of formulas or anything like that. I don't think there's very many in this one, but any type of constants or things like that or conversions would be probably provided for you. Any questions on that? Okay. So then we're going to go off to chapter 14 next. We'll just kind of get a look at it real quick. Do a couple things here. Let's do that maybe. Let's do that. And 14. Okay, so chapter 14 here, and hopefully it looks full size, I hope. Yeah. All right, here's do that. All right, so chapter 14 is about acids and bases, and we're going to kind of cover some things that perhaps you learned back in maybe Chem 3. I don't know if you do acid and bases too much in Chem 1A, but then we'll get into some equilibrium involving acids and bases as we obviously go through this chapter as well. So let us talk a little bit about acids and bases and some things that you hopefully should sort of know in terms of just nomenclature of acids. So let me give you the 2 minute Cliff Note version of acid nomenclature just in case you forgot. I'll try to remember myself as well. But basically, acids will have one of two forms. If you have an acid with, and it's really all about oxygen, right? So if your acid has no oxygen in it, it will have this sort of naming. It'll be something hydro, something ic acid, right? And so if you had HCl, that's hydrochloric acid. You have HBr, that's hydrobromic acid. So, what makes this an acid versus, say, hydrogen chloride or hydrogen bromide? It is actually the state that it's in, which is AQ. AQ is aqueous. It means it's a water environment. And that's really what an acid is, as we'll talk about, is really the ability to make H plus floating around in solution. So that's why we know when we see the aqueous symbol next to an acid, which should always be written next to a formula that's an acid, that indicates that it is an acid and is not something like hydrogen chloride gas, which would have a G symbol next to it for gas and stuff like that. Now, if it is yes, my acid has oxygen, it's going to contain one of everybody's favorite things, right? One of those polyatomic ions. And if you remember those polyatomic ions, they end usually in 8 or 8. So if your polyatomic ion ends in 8, you name the acid something ic acid. So HNO3. NO3 is NO3 minus, which is nitrate. So this is nitric acid. H2SO4. SO4 is SO4 2 minus, which is sulfate. This is sulfuric acid. If your polyatomic ion, I'll go this way, ends in ite, ITE, it is something OUS acid, like HNO2. NO2 is NO2 minus, which is nitrite. This becomes nitrous acid. So that's your quick 2-second how to rename these things. Again, hydro is only for acids that do not contain oxygen. If it contains oxygen, sometimes referred to as a oxyacid, and it will either end in ic or us and not have hydro in it. Any questions on that there? All right, so bases are usually just named like normal sort of nomenclature, but these are sort of the acids. You should hopefully know this and obviously know how to name acids, because sometimes we will come across problems where they just simply give you the name. So you need to be able to obviously figure out the formula to be able to write the correct reactions. A couple of things about acids. Acids have a sour taste. You shouldn't taste it unless it's edible acids, I suppose, like vinegar. Is basically acetic acid. Citric acids contains citric acid. They react with certain metals to produce hydrogen gas in a single replacement type reaction. Like if you take some zinc and a little bit of hydrochloric acid, zinc's going to come in and kick out the hydrogen, going to make zinc chloride, and you're generating some hydrogen gas. That's bubbles that you see when you do this. Properly balance it, I suppose, is the right thing to do there. So we'll produce this in a single replacement reaction. Again, hydrogen displacement, basically kicking out hydrogen. When hydrogen comes out, it comes out in its elemental form, which is hydrogen gas. They also react with carbonates and bicarbonates to produce carbon dioxide, also in a reaction you probably have seen before. So if you take some of a HCl plus maybe a little, we'll go with sodium carbonate, why not? Basically a double displacement reaction between these two guys. And we will make something like H2CO3 plus some sodium chloride. Guess also should put a 2 there as well, maybe a 2 there. This is a double displacement reaction. Again, the hydrochloric acid is positive, negative, right? This is positive, negative, two positive guys swap partners. But what ends up happening, this is a double displacement reaction followed by a decomposition reaction, because that is carbonic acid, CO3 2 minus carbonate. Carbonic acid will very quickly decompose into H2O and CO2 gas, which is how we produce that gas, like the plot, plot, fizz, fizz, Alka-Seltzer type of deal. Kind of a similar situation. We produce that sort of CO2 gas that you produce based off a decomposition that's happening with carbonic acid. Any questions on that there? Bases, they have a bitter taste. Also, probably shouldn't taste bases. They feel very slippery. A lot of soaps, drain cleaners are bases, like sodium hydroxide and stuff like that, are bases. A lot of bases oftentimes will have hydroxide in it, OH minus. And a lot of things on the periodic table in group 1 and 2, those are a lot of strong bases come from. All right, so we got a little bit into it. We'll stop here then. We'll take a 15-minute break. We'll start about 1 there for lab. And up on today's lab is really